Hello and welcome to Machine Learning First Steps. So today we're going to introduce the problem of binary classification and logistic regression algorithm. So this basically reminds me of that scene in the Matrix where Neo saw a cat, but he saw it twice and understood that there was a glitch in the Matrix because he saw the same thing twice. So how was Neo able to see that there was an example that was repeated before him in the Matrix? So how was he able to classify that that was the same cat that he saw before? This is basically the foundation of our problem today. How are we going to classify an object based on some training examples that we've seen before? So I'm going to present this little lecture to you. And by the way, I'm Samer. So what are we going to do in this tutorial? We're going to understand the theory of binary classification and how we're going to use logistic regression to solve that problem. We are also going to understand the importance of classification for robotic applications, since a lot of robotic applications and self-driving applications rely heavily on classification and detection in order to navigate more complex autonomous system schemes. So, let's go. So now we're going to deal with a new problem known as binary classification. So what exactly is binary classification? Binary classification is the problem of trying to classify something into one of two classes, which are basically true or false. So imagine that we have, for example, an image of a dog, for example. Not the best drawing, but we can go with that. So imagine that I want to classify this image as being the image of a dog or not. So I'm going to say true if it happens to be the image of a dog, or false if it's not. So how am I going to present that mathematically? So in order to do that, we first have to understand how images are formed. So basically your image is saved on your digital device in a format which is called an RGB format. So this basically means that your image is composed of three different matrices, one for the blue color, one for the green color, and one for the red color. So basically each of these matrices has rows and columns that look like this, and each element of each matrix has a value that is called the depth, which ranges from 0 to 255. So basically, this number here represents the strength of that particular component in that particular location in the image. So for example, if I have very high value in a certain element in the blue matrix, for example, then that means that the component or the blue component of that image in this particular location or this particular pixel is very high. So each of these elements represents a feature, basically. The same thing goes for the green matrix and also the red matrix. So it is logical to say that since these elements represent features, we can take them as the inputs of our new algorithm. So how are we going to do that? First of all, we learned in our linear regression problem that inputs are taken as Coulomb vectors. So basically what I need to do is to flatten out all of these matrices into a singular vector. So what I'm going to do is I'm going to just collapse this matrix into individual elements and then regroup these elements in a singular vector. So for example, if I have a matrix which happens to be of the size 3 by 3, which is pretty small for an image, but we'll take that as a mere example. So I'm going to have basically a vector that is going to consist of 9 elements, or 9 times 1, if it's a Coulomb vector. And next, I'm going to append the green components to that original vector, so we'll have another 9 times 1, and the red component, or the red elements, so another 9 times 1. So basically, this is going to represent the input feature x for a specific example or a specific image. So what we need to do now is to map this x using some function into y. So we gotta ask ourselves how y looks like. So basically, for binary classification here, we need to indicate whether the image is true or false, or whether this example is true or false. So basically, y has to assume one of two values, either 1 or 0. So this is quite different from the linear regression problem, where y could assume so many values. So basically, y has to be either 1 or 0 for each example. So now we can decide the shapes of both x and y. So basically, if we think of x, we can say that a singular example, or a single example of x, would be some vector or Coulomb vector for a specific example. So let's just say this is x1, which is basically the features of the first image. But since we like to vectorize stuff or adopt a vectorized implementation for applications in Python, for reasons that we mentioned before, I need this to include all the examples simultaneously. So instead of having just one vector x, we're going to have a very huge matrix x, which is going to include all examples. So I'm just going to append the rest of the examples to the first example. So I'm going to have the second, or the input features of the second image, and all of the other vectors up until vector number m. So instead of having a vector, I'll be having a matrix of size n, where n represents the number of features, and m, where m represents the number of examples. And the same logic applies to y. So we're going to have y as an array of zeros and ones. So basically, we have y1, which is y for the first example, y2, second example, and up to ym. And the shape of y is going to be, let's just say y.shape here, is going to be equal to 1 times m. So basically, we decided the sizes of our inputs and outputs. So let's talk about the problem of logistic regression itself in terms of the algorithm that we're going to use. So first step is to decide a suitable function that could map our input feature vector x to the output vector y. So since we now have like an input matrix, so I'm going to say the input matrix x instead of the input vector x. So basically, we need a function that could assume the values 1 or 0 depending on the input. So we might think of something like this. This is called the Heaviside function, which assumes one of two values: 1 if true, or if x is greater than 0, or greater than or equal to 0, and 0 in case x is less than 0. So This function sounds okay, but the problem with this function is it is a discontinuous function. It has a discontinuity at 0. This is basically the function jumps right from 0 to 1. And this represents a problem in terms of calculus, because we can't compute the derivative at the point 0, or at x equal to, or at x equal to 0. So what we're going to do instead is we're going to adopt a function that is very similar to this Heaviside function and at the same time is continuous. So we're going to pick a function called the sigmoid function. And the sigmoid function looks like this. So basically we have our x-axis. I'm going to call this the z-axis now instead of x. And we have the output, which is y. So the sigmoid function looks like this. So it is very close to 0. As long as z is less than 0, then it increases a little bit till it approaches 1 at positive infinity and 0 at negative infinity. And it intersects the y-axis at 0.5. So basically this is very close to the Heaviside function that we've shown earlier, and it is a continuous function, so it sounds fine. Besides, it assumes a value that is very close to 1 once z is sufficiently greater than 0, and assumes a value of 0 of if z happens to be much less than 0. So this sigmoid function can be mathematically represented as follows. So we've got sigmoid of z, which is equal to 1 over 1 plus e power negative z. So if z is large or sufficiently greater than 0, then this means that sigmoid z will be almost equal to 1. And if z is small, that is much less than 0, then sigmoid z is going to assume a value that is very close to 0. So now that we've defined this function that we're going to use, we need to reformulate our prediction algorithm. So for linear regression, we learned that if we have an input x, we can use a linear function here. For example, w transpose x plus b, and then get our y, which is our hypothesis. And I'm going to add a cap here to indicate this is not the ideal y, but instead it's just an estimation or a prediction or hypothesis. So what I'm going to do now for logistic regression, and since I need y to be either close to 1 or 0, I'm going to add a sigmoid unit here, which is going to take the output from the last phase. So I'm going to assume that the output of this linear equation is some variable z that's going to pass and be fed to the sigmoid function here, and then produce the output, or y cap, which is the prediction. So far so good, but we need to determine how are we going to optimize our weights based on this particular function. So the first thing I need to do is to define a proper loss function for each example. And this loss function has to be convex, which means it has one global minimum, and at the same time represents the actual error that we're trying to minimize. So in order to do this, we specify a function that looks as follows. So we've got y cap on y as inputs, which is basically our hypothesis and our outputs, and we get something like this: negative y log y cap plus 1 minus y log, I ran out of space, so let's just retype it. So this loss is going to be negative y log y cap plus 1 minus y log 1 minus y cap. So one thing we need to consider here is this log is actually not the decimal log, the log was with base 10, but actually it is the natural log, natural logarithm, len. So the only reason we're not using the mathematical symbol for natural logarithm is that our programming language, Python, considers log as the natural log. So instead we just write log here, but we need to take care and we need to consider that this log is actually a len, which is the natural log. And the reason we picked this function, first because it is convex, so it has a global minimum, and at the same time it represents the error. So one might ask how it actually represents the error, or how does it represent the error. So we're going to give some example here. If y happens to be true, so it's going to assume the value 1. In this case, the loss function will be equal to negative log y cap, and the next term will be eliminated because we have 1 minus 1, which is 0, and we have negative log y cap. So if our prediction is true, which means it matches the ideal case, so if y cap is equal to 1, then we've got negative log y cap, which is 1, which happens to be equal to 0, which means the loss is 0, or the loss is very low, considering that y cap never assumes the value 1, just like assumes a value that's very, very close to that. So we'll just say 0.99 or 0.98 or something like that. So basically, the loss will be very close to 0. And if the y cap variable happens to assume a value that is equal to 0 instead of 1 or close to 0, then we have negative log, which is actually len, of 0, which happens to be positive infinity. So that means that this is y is equal to 1, and if it is 0, which is pretty far from y equals 1 or pretty far from the ideal case, then that actually will be almost close to infinity, which means the loss is very large. But actually, as we said, we never get like solid values, so it's going to be something like 0.01, 0.1, something like that, but it's going to be pretty close to 0. And on the opposite side, if we got y is equal to 0, which means this this image or this input does not belong to the class we're searching for, then we will have a loss that is basically equal to 1 minus 0. So that's going to be 1. So it's going to be negative log 1 minus y cap. So if y cap here happens to be 0 as well, then we get a loss that's basically equal to 0. So we'll have two options. Y cap is equal to 0, which means it matches the ideal case. So in this case, we get a loss that is equal to 0, or y cap is very close to 1 or almost equal to 1. Then we get, again, a loss that approaches infinity. So this is the good thing about this function. It indicates the error, and at the same time, it offers a very good indication of the amount of loss that we have, and also it is convex, which means it has one global minimum. So eventually, if we try to minimize this function, we'll eventually reach a point which is considered to be a critical point or an optimal point in terms of the classification process. So as we said before, the loss function is only an indication of the error for one example. So what if we need to include all examples? This means we have to pick a cost function. And intuitively, this cost function is going to be the average of all of these individual losses. So I'm going to say that our new j here for logistic regression will be equal to 1 over m multiplied by the summation starting from 1 up to m of all the losses y cap I. yi is going to be a function of every individual example's prediction and ideal output. So this is going to be equal to negative 1 over m multiplied by the summation of I equals 1 up to m of the following expression, which is yi log y cap I plus 1 minus y I. I'm going to just append this here. Log 1 minus y cap I, and then just close my bracket. So now we have a prediction function, which is this thing here, and we have a cost function, which is this j. So now we need to develop the optimization algorithm for this particular function. And we're going to use the same approach that we've used before, which is gradient descent, since we have a convex function that we can apply gradient descent to. So basically we're going to repeat the same steps we did before. So we need to compute the partial derivative of j with respect to some wk, for example, which indicates the kth weight. And then we're going to use this to update the weight through this equation. It's partial j partial w. And we can say this is k plus 1, for example, which means the k plus 1 iteration. So in order to do that, we need to compute some derivatives. So how are we going exactly to do that? So this is where we use some simple rules of calculus. Actually, one rule, which is known as the chain rule. So first of all, we know that we have some input features, x, for example, or x's, up to xm, that are fed and multiplied by some weights, for example, w1, w2, w3, whatever. And there's an offset as well, which is b, which happens to be multiplied by 1. And this produces z, which is basically going to be equal to all of these weights multiplied by all of these input features. And finally added to b. Then we have something called an activation function. So I'm going to denote this by a. So I'm just going to say there's a variable a here that's equal to the sigmoid of z. Then finally we have a loss function. Well, let's just say, all right, let us pick the loss function, since we're considering one example right now, which is function of a and y. So basically a is the same as our hypothesis, basically, and y is our ideal output. So first of all, I'm going to compute the partial derivative of L, for example. So partial L by partial A. A is capital, so I'm going to give it that. And if we take the derivative of the sigmoid function, then it will look like this, basically. It's going to be equal to negative y over a plus 1 minus y over 1 minus a. So this is basically calculus, so you don't have to actually derive it yourself. this is going to be the result. You have to trust me on that. So this is basically the partial derivative of L by A. So, which is basically how we get the derivatives of natural logs. So that happens to be like sophomore calculus or maybe freshman calculus. In case you just don't remember that, or in case you didn't, you weren't taught that at all, it's okay. Well, I just derived that function right away and put it here, so you don't have to worry about that part. And the next thing we're going to do is I'm going to compute the derivative of z, the derivative of a with respect to z. So this is going to be basically equal to, this is the sigmoid function, and the sigmoid function is basically equal to itself multiplied by 1 minus itself. So this also happens to be derived from the basic rules of calculus for exponential functions, because the sigmoid basically is like 1 over 1 plus some exponential. So we're just going to accept this as a fact for now. We don't have to derive it ourselves. So what I'm going to do now is basically multiply both, because I need to get like the partial derivative of L with respect to z, for example. Okay. And actually this can be just the derivative, since we don't have like partial elements that we need to take care of. So it's just the derivative of L with respect to A, and we got the derivative of A with respect to Z. So we're going to have just the derivative of L with respect to Z right away. We don't have to use the partial notation. So I'm going to multiply the derivative of L by A by dA by dz, and this happens to be called the chain rule, and eventually that will be equal to the two expressions that I've derived before multiplied by one another. So basically, by computing that, we get the following expression, which is basically A, the activation or prediction, minus Y. So it's pretty simple. So this happens to be the derivative of L with respect to Z. So what we actually need to do is we need to get the partial derivatives of L with respect to each weight. For example, let's denote that by W some subscript. Let's just pick the subscript H, for example, for no reason. So we've got W1, W2, W3 up to Wm, as well as the partial derivative of L with respect to B. So in order to do that, we'll just apply the chain rule one more time. And if we do that, if we get the partial derivative of L, for example, with respect to partial W1, it will look like something like this. It needs to be the derivative of Z with respect, or partial derivative of Z with respect to some W1, and we have to multiply that by partial L. So we need to just include partial L, or dL in this case, dL over dz times partial dz, or partial z by partial w1. So basically, z is a linear function of w1. So basically, the derivative of a linear function can be just the coefficient of that particular variable, getting the derivative with respect to. So basically, the coefficient of w1 is x1, so we get something that looks like this. We get dl over dz multiplied by x1. And the same goes for each weight, so we can say that partial L for partial W at H is going to be dl over dz multiplied by xh, which is the coefficient of wh. And for b, partial L over partial b is going to be dl by dz multiplied by the coefficient of b, which happens to be 1. So this is basically 1. And we'll just get that. So basically, this is how gradient descent works. So if you're going to do the backpropagation step, which means the step of computing the derivatives in order to update the weights, then we're basically going to adopt these formulas or formulae. And the last thing we're going to do is that we need to reformulate that for the entire cost function rather than the loss of just one example. So this basically means we're getting the derivative with respect to the average of the losses rather than just the loss of one example. So this will look like this. So basically, if we need to get the partial by partial W1, for example, of the entire cost function, which includes all the W's and B's, and all the examples or all the input features. So this is basically a function of matrix W or the vector W of weights and B. And this is going to be equal to 1 over m multiplied by the summation starting from I equals 1 up to m of the partial derivative of each individual loss added together and then divided by the number of examples, which is equivalent to getting the average of the derivatives, for example. So that's it. So what we're going to do next is that we're going to use these concepts and try to develop our own code for logistic regression for a classification problem. So we need to classify whether an image is the image of a dog or not. So we're going to use some helper functions. We're going to develop our own helper functions to compute the derivatives and compute the predictions. And then we're going to compare these with a data set of images that is provided for us. And we're going to convert these images into actual NumPy arrays or NumPy matrices. And we're going to execute all these operations in order to train our network. And once our network is trained, we will try to get the predictions of our network and how accurate our logistic regression unit is. So in order to summarize what we did today, we now understand how logistic regression works and how it actually is a reformulation of the previously mentioned linear regression problem. But instead of just using one linear function, instead we're using a nonlinear function. And now we can use our software tools to start on working on our second machine learning project, which happens to be a classification problem. So we're going to classify whether a certain image is actually the image of a dog or maybe something else.